This is Free Range Digital Design, Chapter 23, Example 1. So we've been working with finite state machines. In particular, we've been using finite state machines to design counters. This is another counter design problem. First step in all digital design problems is to figure out what the interface is. So this is a counter of some sort. So looking at this thing, here's the output. It obviously has a 4-bit output. We'll creatively call that CNT for count. This is always going to be a sequential synchronous circuit that has a clock signal. And what else do we have in this one? This has an up input. Now we'll worry about what the up input does in a second, but the input looks like it allows the counter to count up, or it holds. Sometimes up is asserted, counts up, not asserted, counts down. This is asserted, counts up, not asserted, hold. So that needs to be specified in the problem. So next thing here, we have a typical counter problem, and we had a kind of a set of rules to figure out what was going to happen in this circuit. We know for sure what the underlying circuitry looks like, so we're just going to plop it out there real fast. This is our rough model. What it's missing here is the width of the registers. So we look at this thing, we see it has 4 states here because we have 4 different counts. We only need the state registers to be 2 bits wide in that case. And then there's our 2 bits for the next state decoder. And this is, of course, 2 bits also. We can give this cooler names, ST and ST plus. We're essentially done with that circuit. So we've got the outputs controlled. The up is the external input. The up does not affect the output directly. It just allows it to count. This is necessarily a Moore machine. We need this output decoder because we have to translate it from 2 bits to 4 bits, which is not a big deal. But once this count output is not directly dependent upon the external up input. Next step, or we could have done this first, not a big deal, is to model the state diagram on this circuit. So we'll do that. Here's our basic state diagram. What we've indicated is the outputs. It's a Moore output, so we list that count, which is the Moore output. We list that inside the state. We've got all the transitions. We don't have any conditions associated with the transition. When the up is asserted, it counts up, and so we'll list that in there. If up is not asserted, it holds state, and then we can come back and put that in there also. We are officially done with the circuit. Next thing we need to do to make the circuit work is define these 2 decoders. The register is defined quite nicely as it is. So what we're going to have here is state, T, up input, and the next state. This is going to define the next state decoder, and additionally what we want to put in this thing is the count. So what we're doing is combining both the next state decoder and output decoder into the same table. So this is kind of the brute force design approach. Notice that these states, as we've seen before, come in pairs. Remember, this is the state column. So I think I'm going to undo the holds first. So if it's in state 0 and it's held, I'm going to just put that state in here. So here's state 1, 0, 1. This is 1, 0 and 1, 1. So we've handled the case where it's holding. Here's the case where it counts up, 0, 1, 1, 0, 1, and 0, 0. And so essentially that is our next state decoder. Lastly, here we need to put in some values for the count, and so the count is based solely on the state because this is a Moore machine, so it too is going to come in pairs here. And let's do it. So in state 0, 0, and this is somewhat arbitrary. It doesn't really matter how we do it, but it's always best to keep it in order. So in this state right here, the output is 0, 0, 0, 1, 0, 0, 0, 1. Counts up to 0, 0, 1, 0, 0, 0, 1, 0. Counts up again. And there it is. And once again, because it's a Moore machine, these outputs cannot change in the middle of the state. And that's what we see there. looks pretty good. I don't think we've forgotten anything on this one, and we're going to call it done. So notice, once again, state diagram has no mention of clock. The PSNS table, this is what this is, has no mention of clock either. All the transitions are understood to happen on the clock edge. We didn't even put the clock in the circuit diagram. All we did was put that clock signal, and that's good enough. It's understood to be the clock.